Good morning. Well, we're here in CSC323 programming languages. We're going to talk about our last topic, which is the programming language Prolog, but more specifically, a type of programming called logic programming. So, in order to understand what logic programming is, let's talk about what it is not. So, logic programming is not object-oriented, procedural, or functional. The way logic programming works is that a programmer declares facts, relations, and rules. So these are things that must be true. And then the user asks a question or makes a query, and then the system solves the question, and it uses the programmer declarations and also theorem proving and also recursion. So we'll say that the system solves the question using programmer declarations, theorem proving, and recursion. So this is very different from the types of languages that you're used to programming in. The reason why is that you, as a programmer, are not programming the solution to a problem. You are programming things that you know about the domain of the problem that you're working in. The solution to the problem is actually done automatically by the logic programming engine. So it's very different from what we're used to doing when we're programming. We're used to, as programmers, writing, writing the code that solves the problem. Okay, so what we need to do to get to the place where we can have programs that solve problems for us somewhat automatically is we need to look at the various parts that a programmer declares. So we're going to look at facts, relations, and rules. So the first thing we're going to look at are facts. So what are facts? All right, well, these are basic truths in the system. For example, in Prolog, we can say male Albert. Okay, so what this means is that Albert is a male. So the syntax for this, for any truth in Prolog is you have something called predicate, and then you have something called an object. Now, what is a predicate and what is an object are things that you can make up. I just put this term male here, and I put this arbitrary object Albert here. Other than using the word male and using the word object, using the word Albert, there's nothing special about these predicates or objects. Okay, so let's do an example where we create some facts in our Prolog program that we're going to build. All right, so how do you do that? Well, first of all, on the course website, down at the bottom, I have a section on Prolog, and there's an installation link, and if you click on that, it's going to take you to the new Prolog website. And there's a download section. You can click on that, and there's instructions here and software that you can download onto your computer. So once it's downloaded and installed, you can run Prolog and load in facts. So I'm going to actually write a little bit of code to create some facts. All right, so we'll just do VI example. We'll call it, I think I'm going to call it, yeah, we'll just call it example.pl. So you have to be careful here because I'm saying example.pl. Now we've been programming in Perl. We're not writing Perl code here. The .pl stands for Prolog. Okay, so I'm going to create some facts. So the facts are Albert is a male. Edward is a male. Victoria is a female. And Alice is a female. Okay, so those are my facts. And I just saved that. By the way, I was using a different editor called VI. VI, Emacs, there are all kinds of really nice editors that are out there. So I switch back and forth between those. I mentioned before that Shai's probably his all-time favorite editor is VI. Okay, now I have these facts. All right, a file with these facts. Now, how do I use them in a Prolog program? Well, first I'm going to run the Prolog. I think I just say Prolog. No, it's gprolog. All right, so the Prolog's running. And now if I want to load those facts that I that I just created, I'm going to say example, oops, with a period. So I just loaded the facts, and now I can do a query on the facts. I can say, is Albert a male? This is a query. I'm basically saying, is Albert a male? Yes, Albert is a male. All right, is Alice a male? No, Alice is not a male. Is Alice female? Yes, Alice is a female. So that's pretty cool. All right, so let's go back and talk about, so those are basic facts that you can load into the system. The second thing that I said is that I talked about a programmer declaring facts. A programmer can also declare relations. So what does that look like? Well, relations relate to objects. All right, so here's an example. Parent, Albert, Edward. So what did I just say here? I just said, essentially, Albert is parent of Edward. that's what I just said when I did this. So my two objects are here, and this is my relation. So the syntax is some kind of relation name, and then object 1, comma, object 2. Okay, so what I'd like to do then, given that that's how you define relations in Prolog, I'd like to create the following relationships. I'd like to have Albert and Victoria. They're married and they have 2 children, Edward and Alice. So I'd like you to go back on, or you can do this in your notes. I'd like you to go to the example.pl file and add the relations to let Albert and Victoria be the parents of Edward and Alice. All right, so take a second to hit pause, then take a second to do this, and then let's see if we have the same answers. Okay, so in order for this to work, I'm going to say parent Albert. Albert is the parent of Edward. Okay, we did that already. But the other parent of Edward is Victoria. So Victoria is the parent of Edward. And I also want to make Albert the parent of Alice and Victoria the parent of Alice as well. Okay, cool. So I'll save that. We'll run Prolog again. We'll load the example file. And then we'll say, is Edward the parent, is Albert, sorry, Albert the parent of Edward? Well, yes, true. That relationship is true. All right. Is Edward the parent of Albert? No, that is not true. Okay, so you might be thinking, this is a pretty stupid language. If all it does is basically report that a relationship is true or a fact is true, if you type it correctly, what could it possibly be used for? Well, now we're about to take a step into some cool stuff that Prolog is capable of doing. So let's go back here. And we're going to talk about variables and unification. Okay, so we can create more powerful queries. All right, if we say female and then X, period, what we're doing is we're saying use unification to find all values of X that make female X true. So what does that mean? Well, what are the values that make female X true? Well, if we say X equal to Victoria, that would make female X true. If we say X equal to Alice, that also would make X true. So let's give that a try back here. All right, female X. Victoria. And then okay, so if you just press enter, what it will do is just give you the first X that satisfies your query. If you do semicolon, it'll give you additional ones. So in this case, we just have Victoria and Alice, so only 2 are satisfied. But if you just keep hitting semicolons, you'll see other values of X. All right, so that's kind of interesting. How about this? Can you write a query that would find out who Edward's parents are? All right. So using a variable, can you write a query that would find out who who Edward's parents are? Okay. Try that. Hit pause. Okay. So if you want to find out who the parents of Albert are, you can say parent X Albert. All right. And what, whoops. I'm sorry, I screwed that up. Parent X Edward. There are no parents of Albert. So Albert is a parent of Edward, and Victoria is a parent of Edward. And I did the semicolons, and now we have no other things that satisfy the query. So that's pretty cool, right? So it's almost like we've set up a database of facts and relations, and then we can do queries against that database. All right, so let's go back to the notes here and just talk about this a little bit. How does this work? Well, it does a simple scan of facts and relations, and it does pattern matching to eliminate impossible matches. So for example, if we're looking at parent Edward's parents, we're going to skip parent Alice. So we've got some, some performance improvements there. Okay, a few things about syntax. You must capitalize variable. You must lowercase constant, and you must lowercase constant objects, and you must lowercase constant, I guess I said this, we'll do it this way. You must lowercase constant objects, relations, and predicates. So when I say female X period. This variable x is capitalized, and the the predicate female is lowercase. Okay, so let's go back again to our list here. The programmers declare facts. We talked about how to do that. Rules, facts, relations. But now we need to talk about rules, how rules are set up. And we actually looked at how a user can ask a question or a query. Okay, so let's talk about rules. All right, so we have to spend a little bit of time talking about how rules are constructed. So rules are constructed using something called a horn clause. And the basic idea of a horn clause is that you have something here, C, which we're going to call a consequent or head. And you have a list of one or more these are conditions, H1 to Hn, and these conditions are ANDed together. So these are conditions, or we call them antecedents, or the tail, and these are ANDed together. So all of these things must be true for the consequent or head to be true. All right, so let's take a look at how we would do this. All right, so here's a simple horn clause: male Albert. All right, this is basically a horn clause without a tail. Here's another one: parent Albert Edward. This is also a horn clause without a tail. All right, so let's look at one that's a little more interesting. All right, father Albert Edward. All right, so this syntax is, you type this in exactly as I'm doing it, a colon with a dash after it. So this is our head, and now we're going to do our tail. All right, and so Albert is the father of Edward if the following things are true. What has to be true for Albert to be the father of Edward? Well, first of all, male Albert. You can't be a father unless you're male. Oops, I don't use that period. All right, and then the other thing that has to be true is that I'm running out of space here, but so I'll write it down in the next line, but they would all be on the same line. Albert also has to be a parent of Edward. So these two clauses or antecedents must be true for Albert to be the father of Edward. Albert has to be male, and Albert has to be Edward's parent. Then we can say that Albert is the father of Edward. Now, things get interesting when you use variables instead of facts and relations constants. So things get interesting when you use variables instead of constants when you're defining these horn clauses. I mean, we could make the idea of a father much more generic, all right, using variables. Okay, so here's how we could do that. Father x comma y. So here we're saying x is the father of y if the following conditions are true. First of all, what has to be male? Well, x has to be male. And secondly, what about the parent relation? Well, x has to be the parent of y. That makes complete sense, right? This is kind of exciting. Why don't we do this? Why don't we take a look at seeing if we can add this rule to our list of facts. I just paused that. No, let's pause. Yeah, I don't know if this is going to work, but we'll try it. All right. Father x comma y. Okay, if, oops, dash. If I'm not going to be too clever with the spacing here. If x is male and x is the parent of y. All right. So but let's take a look at what would satisfy that. So x has got to be male. So Albert and Edward are both male, but x must also be the parent of y. So the way the system's going to do this is it's going to start looking at facts, and it'll probably start with this fact and say, okay, what are the values of x that satisfy male? There's two, Albert and Edward. So let's deal with Albert first. What are the values? Okay, so we know our x is Albert. Okay, so that's true. So we found one where male x is true, male Albert is true. So now scan parent and see if you can find values of x for parent. Well, we have two. This one, Albert is the parent of Edward, and another one, Albert is the parent of Alice. So what it will do is it'll say, okay, well, we have Albert being the parent of Edward, and Albert is, so that's true, and Albert is male, so that's true. So we have something that would satisfy father XY. And the same thing is going to happen here with Albert being the parent of Alice. Albert is male, and Albert is the parent of Alice, so that's another satisfaction of this particular rule. So let's see what happens when we try to use this. Okay. We'll load example. And we'll do this. Father, Albert, comma, Edward. You know, is that true? Let's see if that's true. Yes, that is true. Okay. Father, Albert, comma, Alice. Okay, that's also true. Okay. So let's try father, Albert, comma, Y. Who is the father, who is Albert the father of? That's what this query is saying. So let's see what happens. Well, it's saying Edward satisfies father Albert, and Alice also satisfies father Albert. Now think about that for a second. First of all, this father Albert Edward and this father Albert Alice, neither of those exist in our database. right? All we have here is father x, y. But yet we were able to satisfy this and come back with a true, that this is actually a rule that can be satisfied. We also were able to use a variable here, Father Albert y, and we were able to allow the system to do some processing using unification and some backtracking, actually, to satisfy what values of y would Father Albert y be true in, and that was Edward and Alice. So let's look at this in a little bit more detail. How does this process work? So the question we're asking is, how does this work? All right, so we're going to take facts, relations, and rules, and we're going to do unification and backtracking. To make this work. So first of all, if we say father f comma Edward, what happens when we do that? Well, it creates at least a partial set of antecedents. So the first one is male f, that must be satisfied, that must be true, and then parent f comma Edward. So we have some stuff that's filled in. Now, how do we evaluate these until we can get some values that are true? Well, think about this. We're going to scan our database for male f, all right? Values of f where male f are true. And so the first thing the database is going to do is it's going to say, okay, well, male Albert is true. Okay, great. So if male Albert is true, then we've taken care of that. So now let's scan the database for parent f, where f is Albert, Edward. Do we find that? Yes, we find a parent Albert, Edward. And so we've reached a goal state. And we can return f equals Albert. Okay, cool. Are we done? No. Once we've reached the goal state, are there any other parents, are there any other male f's that could be satisfied? And the answer is yes, there is another one. There's male Edward. And so if that is true, male f, where f is Edward, is true, is there a parent f Edward? In other words, is there a parent Edward? And that's going to fail. There is no parent Edward, and so we don't get a goal state there. And so we're left with, for this particular query, f equals Albert. That's the only goal state that we're able to reach. All right. So, what if, so if that's the way things are processed, what if we just do make a slight change, all right? So what if we change just to get a better understanding of this unification and backtracking, how it works, what if we were to do this? What if we were to create a different rule, same effect, father x, y is defined as parent x, y, and then male x. All right, so all we did is we switched these antecedents. They're also called subgoals. All right, so here's our query then. Father F, comma, Edward. Okay, so we know that we can partially satisfy this by filling in our constant. So parent F, comma, Edward, and male, whoops, let's go back here. And wow, that was cool. And male F. All right, so how would this work? Well, the first thing we're going to do is we're going to scan the relations, and we're going to look for matches between parent F, values of F that satisfy parent F Edward. So the first one we'll encounter in our database is parent Albert Edward. Okay, so that's true. So now, if F is Albert, we're going to look for our second subgoal. Can we find a male that is Albert? So male that is Albert. We can. So we've reached our goal state. And we can return a value of F equals Albert. I want to say Aldert for some reason. All right. Also, there's a second match of parent, a second match of parent F Edward. Can you figure out what that one is? Take a moment, hit pause. Okay, if you're following along with me, the second one is parent Victoria Edward. And that, in that case, F is Victoria. And so the question is, can we go to the second subgoal and find male Victoria? No, that does not work. And so this is a failed pursuit of a second possibility. And so when we're done, we're going to end up with the solution F equals Albert. But it happened in a different way, right? We checked the parent relations before we tried to do the male facts. All right. So let's take a look at another one that's even a little bit more interesting. So I'll do the query first here, and then we'll talk about how it gets satisfied. All right. We'll load example. Now, what if I were to say, father F, comma, C. So father F, C. All right. Wow, this is a little bit more complicated, right? So it says, well, if C is Edward and F is Albert, that satisfies. If C is Alice and F is Albert, that also satisfies. And that's it, which makes total sense. Now the question is, how does this work? How does this actually work using unification and backtracking? Okay, so let's take a look. The tree gets a little bit more complicated. So here is our query, father F, comma, C, and that is going to trigger the evaluation of parent F, comma, C, and male F. Now, how do I know that? Well, if we go up here and take a look at the rule that we set up. That's the rule that's in the database. So the system is going to attempt to satisfy that rule by generating this set of antecedents that have to be satisfied. Now, there's no constants in here, and so there's a little bit more work that's involved. And so the way the work it gets evaluated is we do unification first. We attempt to find values of f and c that satisfy parent. And those are basically the relations that are in the database. All right, so the first one will be, the first one is going to be parent Albert, parent Albert Edward. I'm writing a little smaller here. Whoops, I just noticed that you didn't see the screen. Sorry about that. So parent Albert Edward, and then male Albert. So F here is Albert, C is Edward. When that's satisfied, we're going to attempt to find a male of F, a male of Albert. And we do find that, and so we reach a goal state where F is equal to Albert and C is equal to Edward. Okay, so that takes care of the first parent, Albert Edward. Now we're going to try to satisfy the second one. We find a parent of Victoria. I'm sorry. Yeah, well, the order depends on how we set in the database. So I think we did Victoria next. So Victoria Edward and male, this is F and C. So we're going to attempt, once we found parent Victoria Edward, we're going to attempt to do male of Victoria. And that will fail. All right, so we'll backtrack back up again and see if we can find something else that satisfies parent FC. We have parent Albert Alice and male, this is F, this is C, so we're going to have male F, so male Albert. And that is a goal state. So F is equal to Albert and C is equal to Alice. And we have one last one that we have to try, and that is parent Victoria Alice and male, this is F, this is C, and male Alice. And that fails. All right, so a little bit more complicated. Okay, so this is demonstrating unification and backtracking. The unification part is the initial discovery of that first rule that in the antecedent that is true. And that sets up values for F and C that can be used in following antecedents. Once we find that that rule is satisfied, we then continue processing the antecedents to see if we get a match. Now, the thing about this is, if we don't get a match for male Albert, whether we get a match or not, it doesn't really matter, but once we're done processing those antecedents, we can backtrack. We can backtrack and try other rules or facts that satisfy that first antecedent. Now, this discussion assumes that the satisfaction of the antecedents is deterministic, but in a true logic language, they don't have to be. In other words, this doesn't have to be the first one that gets evaluated followed by the second. It could be followed in any order. Okay, so why don't we try making a rule that you, I want a rule for, that I want you to write a rule, all right? And so here's the rule. So I want to write a rule called child of. And if I specify a variable here and I say Victoria, what I will get back is list of children of Victoria. So I would like you to write this out. I'll get it started for you. Child of X, Y. So we're saying that X is a child of Y if what antecedents or sub-goals are true? What do we have to put in the tail to make this true? All right, hit pause, take a second to think about this, hit pause, and then come right back. Okay, so the answer to this is we just need to flip things around a little bit using parent, because that's how we determine if something's a child. So if we say parent y, x, we've satisfied the query, right? X okay. X is a child of Y if Y is a parent of X. That should make a lot of sense. Okay, so I have a class exercise for you all to work on, all right? I want you to answer the following, and the way I'll do this is you can sort of code with me. So we'll get out of here. All right, so I'm going to add some cool data here. So I want a rule for brother. And I want a rule for sister. And I want a rule for uncle. And I want a rule for nephew. And a rule for, oh, I see, I'm missing one here. A rule for aunt. And a rule for nephew and a rule for niece. Okay, so I'd like you to write those rules. Now, the nephew and niece ones are a little tricky. And so what I'd like you to do is work on those and then think about nephews and nieces a little bit. One of the things I'll tell you, just as a hint for nephew and niece, is that you can have multiple rules. And if you have more than one rule, it basically is sort of like an or of the tails. So one of the rules has to be true, or both of them can be true. But if one is false, if one of the tails is false and the other tail is true, that's okay. And to have multiple rules, you just define the rule multiple times. All right, so for nephew and niece, you're definitely going to need to do that. Okay, so don't be passive. I want you to try and write these on your own first, and then come back and we'll talk about them. Now, in terms of data, to try this out, if you go to the course website, let's see. If you go to the course website, I have a program that says family.pl, and this program contains it contains a list of family and the relationships between the family. So I'll show you what that looks like. Not relationships, but just family information. Okay, so there's a lot of data in here. We've got parents, like lots of cool relations here. You don't want to type this stuff in. So you definitely want to download that family.pl, all right? And I'll show you how to use that. I think you can load multiple, I don't know, let me think about how we want to do this. So I think what I'm gonna do is just cut and paste that family information in here, starting here. So here's how I'm gonna do that. Oh, this is kind of cheesy, but okay. So I just concatenated the contents of my example.pl onto family.pl, and then I renamed it example.pl. So I'm gonna look at example.pl now, and you'll see that everything's kind of stuck together. Huh, there's some annoying control M's there. I don't know what those mean, but I might have to delete those. Okay, so these are all the cool facts. I've got some duplicate facts here with Albert and Alice and that parent information. That's duplicative. Okay, but all the rest of these are things that we want to fill in. So take a second, fill this stuff in, and let's see where we're at. Okay, hit pause. All right, I'm assuming you made an attempt at defining these, so I'm going to define them as well. Now, what does it mean for X to be the brother of Y? Well, one of the things that's true is X definitely has to be male. The other thing that's true is that X has to be a sibling of Y. Huh, I better define sibling then. What does it mean for X to be a sibling of Y? Well, if X is a sibling of Y, it means that that we have a relationship between X and Y so that they have the same parents. So we would say that we have some parent Z, and that is the parent of X, and that parent Z is also the parent of Y. So that takes care of sibling. All right, so if X is male and X and Y are siblings, then we can say that brother XY is a rule. Brother XY is true. All right, we got the same thing for sister. If X is the sister of Y, then X is female and X and Y are siblings. All right, what about uncle? How do we know if X is the uncle of Y? How do we know that X is the uncle of Y? Huh. That one's sort of interesting, all right? So if X is the uncle of Y, then X needs to be the brother of some other person, Z, and then Z needs to be the parent of Y. So you think about how that would make sense, right? Let's say that X and Z are siblings, okay? So X and Z are siblings. Well, that means, but in order to be an uncle, you can't just be a sibling, you have to be a brother. So now X and Z, there's a relationship where X is the brother of Z. Okay, now in order for X to be an uncle, not only does X have to be the brother of Z, but Z has to have some child, or Z is the parent of some Y. So this would satisfy uncle. All right, let's do aunt. So for aunt, we would have sister X, Z, and then parent Z, Y. X is the sister of some Z, and Z is the parent of some child Y. Therefore, X is the aunt of Y. Now, nephew is kind of interesting. So the way nephew works, right, for X to be the nephew of some person Y, we would want to have X be male, that's for sure. And what else? Well, we would want Y to be the uncle of X. Well, that's definitely a nephew situation, right? If X is male and Y is the uncle of X, that would definitely be nephew. But we can also have another type of situation where we have a nephew, and that is where X is male, but Y is the aunt of X. So we have to have both of these rules in place. And this creates what's called a disjunction. And the way this works is one of these two tails has to be true. Either X is male and Y is an uncle of X, or X is male and Y is an aunt of X. And so niece is going to work the same way. For X to be a niece of Y, we're going to have X be female and Y be the uncle of X. Or X is male, sorry, X is female, and Y is the aunt of X. All right, so we have a whole lot of data now. Let's try running Prolog. I don't know if it's going to like those control M's or not. We'll try. See what happens. Cool, it was okay with those. I have no idea what those are, how they showed up in the file, but anyway, they're there. I suspect it's some kind of Windows DOS thing, but because I think that's where I created those programs originally. So now we can do something interesting. So let's see. Well, from our original data, we can ask a question. Is Edward the brother of Alice? That should be true. Okay. How about brother Edward X? Who is X the brother of? Well, actually, X is the brother of, Edward is the brother of himself, and Edward is also the brother of Alice. Now that's sort of interesting. Why is it that we got 4 answers, and one of them is kind of silly, right? Edward is being the brother of Edward's self. Well, let's take a look at the rule for brother. Get my screen back up here. So our rule for brother was this. We said, whoops. We said brother X comma Y is male X sibling X comma Y. And we define sibling of X comma Y as, let's take a look. at what sibling was defined as. Okay, so we defined sibling as parent z comma x and then parent z comma y. All right, so let's take a look at how that evaluation works. All right, and then we'll see why we get some duplicate values. So the first thing is, in order to satisfy, what was our initial query there? I think it was, yeah, who is, we said brother Edward, comma, y. So in order to satisfy this, we're going to end up with the beginnings of our solution is going to be male of Edward, and then sibling Edward, comma, y. All right, so that's fixed. Male Edward, that's going to be true. So what we have to do is then we have to evaluate sibling Edward, comma, y. So let's take a look at how sibling Edward, comma, y is evaluated. So sibling, I think I'm going to center this because we might try a bunch of different cases here. So sibling Edward, comma, y. All right, so we're going to now do unification and backtracking and see if we can figure out the solution to this. So sibling Edward, comma, y, well, that is satisfied by, that is satisfied by parent zx. So that's going to be parent, I think I'm going to move this. That's going to be satisfied by parent z, comma, Edward, and then parent z, comma, y. Oh, that's really interesting. Okay, so we have to use unification and backtracking to satisfy these two rules. So if we do that, how is this going to work? Well, first we're going to try to satisfy parent z Edward. Can we find any parent z Edwards? Well, we can. All right, so the first one is parent Albert, comma, Edward. All right, so parent Albert, comma, Edward, that means that Z is Edward, or Z is Albert, X is Edward, and now we have to satisfy, given Albert is Z, we're now going to attempt to satisfy parent Albert, that's Z, comma, Y. All right. So in order to satisfy parent Albert, comma, Y, we're going to repeat this process of unification and backtracking. So parent Albert, comma, Y can be satisfied by the following: parent Albert, comma, Edward, and that is a goal state. And in that goal state, we have X being Edward, Y being, this was Z and Y. So Y is going to be Edward, and Z is going to be Albert. So that's what happens when we satisfy that goal state. Now, the thing that's fascinating about this is because Y is Edward in this case, we are going to return a true, basically saying that Edward is a sibling of Edward. All right, so if Edward is a sibling of Edward, that means that our Y here puts Edward here, and then that means that this Y is Edward. That means that this Y is Edward, and so that sibling Y there is Edward, which means that the brother XY up here is going to be satisfied by Edward. And so that therefore ends up getting us into a situation where we can say, based on the rules that we've defined, Edward is Edward's brother. Not perfect, but it works. Okay, let's continue the evaluation here. In addition to the parent of Albert Edward, we have another parent that is satisfied, and that's the parent of parent Victoria. All right, so with the parent Victoria Edward, do we have another parent Victoria Y that's satisfied? And the answer is yes. We can find a rule that says parent Victoria Y that satisfies Y, and that's parent parent Victoria Alice. All right, and so if we fill everything out here, this is Z, X, this is Z again, and this is Y. And so we've reached a goal state again, and we'll return a new sibling. X is equal to Edward. Y is equal to Alice. And Z is equal to Albert. All right, and the thing that's going to trigger is going to be the sibling that's returned is Alice here, and it was Edward there. We have two other things that need to be analyzed in order to get to our final answer. Okay, so I noticed there's a little bit of an error here. Of course, there's a lot of scribbles here. It looks like it's a little bit complicated. It's really not that bad. But what I've explained so far with the unification and backtracking is how we get the first values of Edward and Alice. But if you notice in the query here, Edward and Alice show up multiple times. Once here, and then a second time. So the question is, why are we getting Edward and Alice to show up twice? The answer has to do with looking closely at the unification that happens in the second antecedent in Edward. So here is that unification, right? I said, is there something that satisfies parent Albert comma Y? And I listed one rule, parent Albert comma Edward, that satisfies that unification. But as it turns out, there is another one, and that is parent Albert comma Alice. And in that case, we also reach our goal And that would be, let's see, Albert is Z, Alice is Y. So X is equal to Edward. Y is equal to Alice. And Z is equal to Albert. We have a similar situation in the exploration of this second antecedent and sibling. We've discovered one parent, Victoria, is the parent of Alice, and we return that as a goal state. But we have a second goal state, which is Victoria is the parent of Edward. And in that situation, Z is Victoria, Y is Alice. We also reach the goal state. X is going to be Edward. Y is also going to be Edward. And Z is going to be Victoria. All right. So that's why we see Edward and Victoria twice, and that's why we see Edward being a sibling of himself.